Today we are going to explore the limits explore derivatives numerically, geometrically, algebraically, and we are going to explore average and instantaneous velocity. So we're going to start with a scenario about my dogs, Ginny and Riley, and they both really like to eat. One day while I was here at school, the dogs broke into my pantry, which I keep closed with a rubber band, and they started devouring a newly opened 30-pound bag of dog food. Through the video that I caught using my nanny cam, I was able to determine how much food in pounds over the course of 2 minutes the dogs consumed. I created a table, which I've shown you below, which shows the weight of food W remaining after time in minutes goes by. W is in pounds and time is in minutes. So the first thing we want to do is compute the total change in the weight of the dog food over the first 2 minutes or over the 2-minute period. We want to show our setup, and then we want to describe in real-world terms what we just found. So the change is going to be basically this Y value of 0.6 pounds subtracting out this Y value of 26.94 pounds. So our setup will just be 0.6 minus 26.94, and the answer will be negative 26.34 pounds. So what does that mean in context of the problem? Well, it means that the dogs, and you have to write a sentence with this, the dogs ate 26.34 pounds of food on the interval 0 to 2 minutes. And the key parts that I have in here, first of all, I included the answer and units with the answer. And then in my sentence, I described what the dogs were doing, so I put in the real-world scenario. Notice that when I said they ate, I converted this to a positive 26.34 pounds. If I had used the negative from the original computation, I would have said that they ate a negative amount of food, which means they would have vomited it up. So you have to be careful when you get an answer and then you put it in context. You have to be careful that you're using the right sign with the number in your sentence. Back to the critical elements of my sentence. I've said what the dogs were doing, I have said the quantity, I have said the units, and I have said the time interval over which this occurred. So now what we want to do is estimate the average rate of change in W, which remember is the amount of food left in the bag, on the interval from 0.4 to 0.6 seconds. So I'm going to go back and use 0.4 to 0.6. Here's 0.4. It should say 1.6. I'm now realizing I have a typo in my work right here. It should say 0.4 to 1.6, so hopefully yours is correct. So I want to go on this interval, or this moment to this moment. I need the average rate of change. Well, the average rate of change is your slope. The average Y value the difference in Y values divided by the difference in X values. So here, instead of delta Y over delta X, we're going to have effectively the second W minus the first W divided by the second T minus the first T. So the setup is going to be 1.28 minus 14.44 divided by 1.6 minus 0.4. Then you can work this out in your calculator and you'll find out that this is approximately negative 10.967, and your units will be pounds per minute. And the units come from the change in W, which is got to be in pounds, because those are the units of W, divided by the change in T, which is in minutes. So that's how we get pounds per minute. And now they want us to describe the real-world meaning of what has happened here. So I'm going to try to change colors ink, and here I go. I'm going to write about this situation and say that on the interval 0.4 to 1.6 minutes, the dogs ate an average of 10.967 pounds of food per minute. Now let's talk again about the critical parts of this. I've given the time interval, including the units, minutes. I'm saying what is going on. The dog's ate. I'm giving the numerical value, and notice that I converted this to a positive away from the negative because I said that they ate, so they ate a positive amount. And then I've got the units, pounds of food per minute. So now we move on to the instantaneous rate of change, and the goal is to approximate the instantaneous rate of change in the weight of food left in the bag at time equals 1.2. So coming up to my chart, I have a value right here at time equals 1.2. But how do I find an instantaneous rate of change if I don't have 2 points? Well, I have 3 options. One is I could take the average rate of change between 0.8 and 1.2. Second option is to take the average rate of change between 1.2 and 1.6. And our third option is to take the average rate of change on 0.8 to 1.6. So I'd either come in from the left, find the slope from the left, find the slope from the right, or find the straddled slope. Any one of these will be counted as correct, and frankly nobody can tell you which one to do because they're all approximations. So I tend to use 1.28 minus 8.5 divided by 1.6 minus 0.8, and that happens to be coming in from the right. There's no rhyme or reason to why I chose this one, but I did. And you don't have to choose the same one as me. You could choose one of the other ones. When I do this in my calculator, I find that this value is negative 9.025, and my units will once again be pounds per minute. So what is this in the real world? Let's discuss it. It's very similar to what we wrote with the average rate of change, but now we're saying at time equals 1.2 minutes, the dogs ate at an approximate rate of 9.025 pounds per minute. So let's talk about what I wrote in here that's important. I gave the exact time at 1.2 minutes, gave the units. Unlike in number 2, I gave an interval because that's an average rate of change over an interval. This is an instantaneous rate of change at a moment, so I give one time. I explained that the dogs are eating, and notice that I wrote it's an approximate rate at which they're eating. I did not have to write approximate in number 2 because I was actually calculating their average rate of change, and I had the data to do so. For the instantaneous rate of change, I don't have all the data, and I'm having to approximate based on the data. I gave the number, and I gave the units. All right, next question is, find the equation of the tangent line to W at time equals 1.2. Well, to write an equation of a line, you need a point and a slope. So the point is going to come from the table. Your time is at 1.2. So going up to the table, we use the point at 1.2. That's right here. So my x value is 1.2 and my y value is 3.11. In calculus, we always write our linear equations using the point-slope formula and not the slope-intercept formula. So you'll need a slope, and then you need x minus the x value plus the y value. Please do not ever use y equals mx plus b. We just don't use it in calculus. It's another one of those situations where it creates errors, and you want to avoid creating useless, careless errors. So using point-slope form allows you just to plug in this point, and then the slope is the instantaneous rate of change we found in number 3. So we use the negative 9.025. That will be the slope that we plug in here. And that is the equation of the tangent line to the graph of the W of t function at time equals 1.2. Now they're asking me to estimate a different instantaneous rate of change. And W prime of 1, this little dash thing here means prime. And that denotes the derivative. which is the instantaneous rate of change. So what they're asking me to do is similar to what we did in number 3, but they want me to find the instantaneous rate of change at time equals 1. So going back up to my chart, now I only have one option in the values that I can choose because 1 is not given as one of the values of t. However, 0.8 and 1.2 are given, and they are exactly on opposite sides of 1. So if I find the average rate of change between 0.8 and 1.2, I can use that as my estimated instantaneous rate of change. So my calculation is going to be 3.11 minus 8.5 divided by 1.2 minus 0.8, and that gets me approximately, well, this calculation gets me exactly negative 13.475, but that means that my instantaneous rate of change, or W prime at 1, is approximately negative 13.475 pounds per minute.